Welcome to our webinar this morning. We're happy to have you join us. Today, we're going to be talking about using Coreform Cubit and Azore for a complete CFD workflow. Now, the presentation today will be by Dr. Jeff Franklin. He is a CFD expert and the lead developer of Azore, and he'll be walking us through this complete workflow to demonstrate just how easy it is to use Coreform Cubit together with Azore for your CFD work. Just a little bit about Coreform Cubit. We're a general purpose meshing toolkit aimed particularly at challenging and difficult simulations. It features CAD import and cleanup, semi-automated hex meshing, and it allows maximum control of your mesh properties and quality. And we also, and this will be demonstrated today, have Python and scripting that helps with automation. And new to Coreform Cubit, for those of you who have not heard, we have some machine learning enabled defeaturing and part classification capabilities. If you're interested in learning more about that, we won't be demonstrating those new features today, but if you're interested, we do have a two-part webinar series that will walk you through those features. And you can find that at coreform.com, support, and webinars. That's it for me. I'm going to turn it over to Dr. Franklin right now for our demo.
So I'd like to really talk about how we can use, and I have a CFD pipeline we're going to talk about today, and we're going to look at Coreform Cubit and how Azor kind of fit within that. To start with, let's just talk a little about Azor. Just for those of you that don't know, it's a CFD software tool. It's powerful, easy to use, accurate. It's an affordable software package. And it is basically a control volume based solver. It's based on modern polyhedral based mesh topologies. It solves, your typical velocity, pressure, heat transfer, all of these things. It's used a wide variety of industries. You can see here, like here's flow over a yacht, a manufacturing plant. It's used in the HVAC industry, data center cooling, green building design, grow rooms, a lot of internal flows. It's also used for external flows like flow over buildings, plume dispersion, and the likes of that. So it is a very capable and easy to use CFD tool, and that's what we're going to kind of discuss today. So going back to the objectives of what we really want to talk about today is the Cubit and Azor workflow, and what exactly is a workflow. So when you're doing a CFD project, you typically start with some sort of project initiation. You conceptualize what you want to do, and then you kind of collect together some software and relationships, and I kind of call it this CFD technology pipeline, where we kind of assemble all these together to gather some information about what we want to know about the physics of fluid flow. And this process, in order to make this process happen efficiently, you want to make sure that you kind of front load it. You want to make some good decisions about the things you do, and so that the next step in the line of things that you do goes smoothly. And that's what we're going to kind of talk about here. If we expand this technology pipeline out a little bit more, we can kind of see how the Coreform Cubit kind of sits on the left-hand side of this pipeline. The pipeline starts with a project initiation. You have some CAD capabilities that you need to deal with, situating your geometry. Then you need to mesh that CAD geometry. You need to set up the simulation in terms of boundary conditions, things like that. And then once all that's set up, you need to set up the solver. You need to pick solution processes, physics. And then once the solution is done, you need to look at the results, the post-processing, the reporting. And then once that's all done, hopefully you have everything you need for the project completion. And here you can kind of see a little bit. So the Coreform Cubit kind of fits on the left-hand side of this diagram, where it really provides the tools necessary to do your CAD work, to do your meshing, and then set up your boundary conditions, whereas Azor kind of sits on the right-hand side of this, where you set up your boundary conditions, your physics, you run the solution, you gather the information, post-processing, and then you're reporting. So that's kind of the pipeline we're going to discuss here. And to kind of facilitate the discussion here, I've kind of chosen two problems to kind of look at in detail. The one on the left are some electric heaters, and this is a simple problem where you have flow coming in, it's going through a duct, we'll call it air, and it's going to pass over some electric heaters right here and be heated up. And so we're going to kind of go through this process, and we're going to kind of drive these software packages, both Cubit and Azore, and I kind of call it the man in the middle, where you're kind of interactively running this software packages to accomplish what's necessary in order to pass through this pipeline. After we've done that, we're going to kind of maybe look at a second problem here, which is a whole shape evaluation. So this is like an underwater vehicle, and perhaps you want to look at many hole shapes. Maybe you want to look at 2 or 3 or 100. And in order to do all of the steps necessary to model that, it might become a little onerous. And so we're going to leverage some of the Python scripting capabilities in Python and just the language in general to set up our simulations using Python and look at how we can kind of automate that process. So we'll kind of walk through both of these. So first of all, I think we'll start with the electric heater problem. And what we're going to do is we're going to kind of look at, and I'm going to start by looking at the CAD. For this particular problem, we're going to start and we're going to assume that we've generated our geometry in a CAD tool, some external CAD tool. And this is the geometry we have here. We have an inlet, we have a square duct, we have some small features right over here, which are the heating elements, and then we have an outlet. But in order to make the meshing process and to really leverage the capabilities in Cubit, we need to do a little bit of extra geometry manipulation so that the meshing algorithms within Cubit can be leveraged and we can really benefit from the capabilities of this tool. And that involves breaking it down into smaller volumes that can be meshed differently. And I kind of have them shown here. We're going to have a large volume at the beginning and the end where the mesh length scales are a little bit longer. But then right around all of these tubes right in here, we want kind of a very small or short length scale for our mesh. So we have kind of cordoned that area off so that we can put smaller length scales and we can kind of use Cubit's algorithms to do that. And then we have two volumes that kind of sit a little above and a little below the heating coils, and we're going to classify that area where we transfer the length scale from a very short length scale to a very long length scale using a tetrahedral mesh. So this is kind of our plan in terms of the meshing of this. So let's just take a little bit closer look at the geometry specifically around these heating elements. There's cylinders here, and we've kind of decomposed that area a little bit more, where we've kind of split those heating elements right here in half, and we have a body up above, a body below, and then we also have these cylindrical bodies. And what we really intend to do in terms of the meshing algorithms is we want kind of a 2D mesh here that is fine, hexahedral, and then we kind of sweep it in this direction to fill the rest of the volume in a 3-dimensional sense. So we have a 2-dimensional mesh that's swept, and we're going to leverage the algorithms inside Cubit to do that. So we've kind of taken care of the CAD side. We've gotten our geometry exactly where we want. And so now what we're going to do is we're going to kind of look at a pre-recorded session where we read that CAD geometry into Cubit and we go through the steps of meshing this geometry. And so here I'm going to start it. And basically we begin by reading in that geometry. And it's being brought in as an ACES file. And here you can see the geometry that we talked about previously within Cubit. And the first thing we need to do is we need to connect all of the faces because we want the mesh topology to be manifold between bodies. So we imprint and merge the faces and then the volumes. So now all of the geometry has been transformed from a non-manifold or manifold to a non-manifold geometry so that Cubit can then generate a mesh. Now we're going to go and mesh the very fine length scales right around the heating coil. So we're going to pick just the elements right around there, and we're going to pick a very small length scale, and we're going to assign to those bodies a small length scale. So now that that's been assigned, we're going to switch the algorithms. We're going to choose a sweeping algorithm, and we're going to ask it to sweep in the Y direction for all of the bodies. These are all the cylindrical bodies right around there. We're going to apply that scheme, and then we're going to ask Cubit to mesh it. You'll notice that Cubit notices that these bodies might overlap. That's not the case, so we say continue meshing. So now that that is done, we're going to go ahead and mesh the larger bodies. And you'll notice that these bodies are squarish in shape. So we're going to pick a little bit longer length scale because that's what we kind of wanted. And we apply the mesh of the length scale there. And so these bodies are square. And so we want to use a submapping algorithm so we can leverage the fact that we want perfectly cubical cells. And then the last thing we're going to mesh are the volumes right above and below these short length scales, and we're going to apply the tetrahedral meshing scheme, and we're going to ask it to mesh it. So now we can kind of take a look of what kind of mesh topology we got. So we have very small length scales around the tubes, so we can capture the physics of the heat transfer there. So the next thing we need to do is assign the boundary conditions. And of course, we have an inlet, so we're going to go ahead and select that surface and name it as inlet. So that so we basically need to cordon off different areas of the mesh topology so that they will become available in the solver so that we can apply boundary conditions to them. So now we select the outlet boundary condition. And now we're going to assign all the walls around the whole surface here. We're just basically using Cubit to pick all of these surfaces. So we're going to name these, basically we want to look at the walls. So we have those. So the next thing we want to do is name the ends of our coils. So we're going to go through and pick each one of these. And apparently there's a new feature in Cubit where you can pick based on size. So rather than doing the tedious task that is recorded here, we might be able to pick those more efficiently with some of the new capabilities that are not in this particular version of Cubit that I was using, or maybe I wasn't aware of them. So the next thing we're going to do is we want to pick the surfaces of the coils themselves. So we hide a couple of surfaces to make it easier for the selection process. And then we go and select these. Slide this along a little bit. We don't need to watch all of that. We're just basically picking all of those surfaces and assigning them. So we've assigned all the external surfaces. The next thing we need to do is assign the volumetric regions in our model that are important and then we want to be able to have access to in our solver. The first group of volumes, the bodies that we want to choose, are the areas where the air is going to be. So we're going to pick all of these and we're going to name them fluid. The next thing we want to do is we also want to treat our elements. We have those solids and we want those in a separate area. And we want to be able to put energy into them because, there's going to be electric current and they're going to get hot. And so we want to be able to do that. So we're going to go ahead and select those very small volumes right there. And you'll notice here when I do the selection process, I'm going to use a drag select here. in a moment. And that allows me to pick many volumes. And then I will deselect some of the volumes because they're larger and more easily selected. And so now we have the section of the volumetrically. So we have external surfaces and volumetric regions now defined for our CFD simulation. So there we have it. Now we go ahead and write out a mesh, and we're ready to go. So we've just watched a pre-recorded session where we took a CAD model that was prepared somewhere else, and we made sure that that CAD model had the features in it that we really needed. We brought that CAD model into Cubit. We meshed it using the algorithms within Cubit, and we set up our boundary conditions. So the next thing we want to do is read that information, that mesh into Azor, and set up and run a simulation. And so here we'll start. This is a session that I have pre-recorded for that. So we start reading in the mesh that was read out by Cubit. And in this part, so basically the mesh is being read in. Azor is converting it, translating it into the file format that it needs in order to interpret it and use the mesh topology. And then as it reads it in, it gives you a little bit of information about what it's doing. So here it is. We can see the geometry as it defaultly shows. We'll quickly take a look at shade all of the surfaces, and we can see that our heating coils are in as we expected it. So the next thing we're going to do is walk through and set the boundary conditions. We're going to use turbulent flow. There's, of course, energy involved. We're going to set our material properties. By default, Azor uses air as a default, so we'll just take those. We're going to set our solid materials inside, and we're going to rename those to coil material because this is the material of the heating elements as they pass through there. So these are solid objects. So we'll make a few adjustments to the material properties of our solid. Changing the thermal conductivity, the specific heat. Okay, so now we've done that. So now we want to set our boundary conditions. So the first thing we'll set are the inlet boundary conditions. This is defining how the air is going to enter. We're going to pick a normal velocity, a nominal 1 meter per second on the inlet. The turbulence we're going to set based on an empirical relationship for the intensity and hydraulic diameter. We'll choose a hydraulic diameter of 0.3 meters, and we'll use the default 300 degrees K as the inlet temperature. We'll take the pressure outlet boundary condition of 0. And just as a reminder here, this is a conjugate heat transfer problem. So we'll notice here in the boundary conditions for the wall that it's coupled so that energy can run from the solid into the fluid, which would be the air. So the next thing we need to do are set the boundary conditions for the volumetrically. And so we're going to set energy source terms in the solid material, and we'll put a large value in there. And that needs to be done for each one of the solids. You can see that it's been done here. The next thing we're going to do is we're going to initialize the solution. And we're going to start running the simulation. One thing since we're kind of doing this interactively, we're going to use this animate data feature, which allows us to look at the simulation while it's running. So we're going to activate that and say, hey, we want to look at the solution while it's running. So we'll save our database. So Azor's database is basically a file folder, and it has basically folders within folders, and there are files in there. Some of them are human readable, and some of them are binary and machine only readable. So we're going to set up, and it's very easy to run Azor in parallel. We just pick the number of processors we run around on, and we save and start the run. So the run is started. And the way Azor works is it's not, the solver itself is not embedded with the GUI. It is run as a background process. And so that process is being started and it's running in the background. And now the GUI and this background process have been connected together and information is transferred between the two of them. So we can actually now ask for the residuals. Can we look at the residuals while it's running? And so now it's run 2 iterations. So we can kind of do some other things while it's running. And since we are connected to it, it might be interesting to look at the solution while it's running. For instance, why don't we look at the pressure on the wall? And we'll push the sync data button, which says, hey, I know, why don't you give me the solution as it sits right now? I want to take a look at it. And this allows you to look at the simulation, perhaps look at it and check and make sure that you've set it up properly. There's nothing unexpected happening. So we can basically, the GUI allows you to very quickly change things. So we have asked it to show the display range. So we see a little bit of a pressure variation as the solution begins to evolve. Not expecting much, it's only 9 iterations into this process. So we can push the button and sync it again, and we can ask for more information. What's it look like after 10 iterations? And it pulls the information over and allows us to look at it. And the graphics allow you to have lighting and shading, and you can look at a lot of various things. It's quite capable. So now I'm going to kind of stop here for a moment and say, well, the simulation has been running for a long time. And one of the important things to remember about Azor, since it's not intimately connected to the solver, you can get out of the GUI and just leave. And so like if Azor is running on a cluster somewhere, wherever your compute resources are, it can be running there. It doesn't have to be connected to the GUI. You can just leave. And so that's what we have done here is we've left it. And now we're coming back at a later time and we're going to reconnect to that process. And here we are, we're going to start doing that. So we're going to open the database again. It's running in the background, we know it is, and we want to check up on it. So it's kind of, we're loading up and checking on again. So it kind of goes through the same process, only it's reading in the database now. And so here we are, we've read it back in. And so now we can go ahead and check on it again and see what the solution looks like again after it's been running for a while. So we can sync the data. And maybe rather than looking at surface data, well, first we'll look at the residuals. So it looks like it's run about 5,000 iterations. It's not quite done yet, but I think it's far enough along that we can really maybe get some information and get a good idea of what is happening there. We're going to put a cutting plane through the middle of the duct so we can see what is happening on the inside of the duct. And we're going to ask to put filled contours on the top of that surface. And you'll notice that they're all 0 right now. So we're going to ask for data to be pulled from the solver so we can look at it. And there we have it. So it's been running a while, and we can see that basically kind of what we might expect. The flow is bunched up on one side of the duct and not on the other. So you see higher velocities, those are the yellow regions on the right side of the duct. We can also look at the temperatures, which is kind of what we're interested in. And we can easily use this slider bar to pick a range that maybe is appropriate to look at. And we can look at it. It's kind of interesting here. We see kind of a hot area on the left side of the duct and a cooler area on the right. And maybe we want to go and explore. It's like, why is it doing that? And perhaps we want to look at the flow structure there on top of this temperature profile. So we're going to ask to have velocity vectors put on that surface as well, so we can get a better idea of what the flow structure looks like there. We're going to kind of interactively choose a length scale for our velocity vectors that would kind of reveal the flow structures. And so we can do that very quickly and easily. And so we can see that the flow is going straight up on the right side of the duct, but there's a recirculation flow on the left side where it's going downward, which is leading to the hotter temperatures there. But you can see where the heating elements are heating this duct. gas. So I think we said, okay, it looks pretty good. We can go ahead and stop the simulation and we'll load the data. And there are many things you can do and look at it. And there, not only can you look at things kind of qualitatively, as we were right here, we can also look at things quantitatively. And what if we wanted to know what is the exact temperature? How much energy did we add? So we can go to reporting and we're just going to simply ask for the temperature as it leaves this. How much did it actually heat up the air by? So we'll ask for the mass flow weighted temperature. And we can report that. So these are very qualitative values. So we can know exactly. So it raised the air temperature from 300 K to about 310. So Azor's GUI allows you to very carefully look at very quantitative values as well as qualitative. So that kind of finishes up that pipeline. So we have kind of looked at the pipeline itself, and we looked at it from a very man in the middle type way where we walk through, we looked, and we kind of drove the software. We made all the decisions interactively going along here. The next thing I'd really like to talk about is let's do this. Let's have this pipeline be automated using Python. And if you remember before, we were going to use this AUV vehicle. This is an underwater vehicle that we want to look at, and we want to look at different shapes, and we want to kind of automate this process from the project initiation on to project completion. So how do we want to do that? Well, we're going to kind of break this up into steps here, and what we really like to do is on the project initiation, we want to kind of gather all of the information that we want to control our project into a simple text file. And that text file will perhaps include the geometry that we want to include, say, for instance, the shape of the hole, and maybe some flow conditions. How fast is it going? What's its angle of attack? Once we have that, we want to use Python to read that information in and then generate the geometry automatically. And once the geometry has been generated, not only will we generate the geometry of it, we will also generate the geometry that is meshable, that we can really leverage the meshing capabilities that Cubit has to mesh all of the topology. And once that's done, we can then use Cubit's Python language to generate the mesh. We can execute the different algorithms. Once the algorithms are done, we will also set the boundary conditions, just like we did with the heat transfer case. We kind of did it interactively. We read the geometry in. We generated the mesh by selecting various things in the menu item. Then we set the boundary conditions. And then once we're done with all of that, we need to set up the model. And this is where we kind of did that interactively with Azor. We read it in. We set the material properties, these things, these type of things. So how do we want to do that? So what's going to be in this input text file? Just for experiment, we'll just say, well, for this, we're just going to see this black line. We just want to pick a series of points right here that represent this shape of the hole. And we can pick, any series of points as long as it represents that, and that will be our input. We'll also say, well, maybe it's traveling at an angle to the flow, and maybe we also want in that file the velocity of, how fast this is traveling. And that's kind of the information that we will have inside this text file that we will use. And so putting together a Python script for this could be involved, the syntax, and it's not just a 1 or 2 lines of code. And so how do we talk about that? And so what I thought I would do is just give a few Python clippets of how one might go about doing that, depending on what you're doing and what you want to do, you will probably make different choices about the exact syntax of your Python script. So for me, I picked an input file class, and I basically made a class, and here I stored information about what's inside that file. How many points are on the hole, and then maybe the shape, the geometry, the coordinates of that, the angle of attack, the velocity. What's the name of the folder that I'm going to create once I have generated the information here? And here's another class. It's just a simple class that stores the XY coordinates, the 2D coordinates of that. And over here is a subroutine that actually reads that file. So we open the file in, we read in all the different lines, and then we have a while loop that kind of walks through and stores all of the geometry information that we want to then use later on. So that's kind of our first step of reading the file. The next thing we want to do is we want to generate the geometry. And there are many commands. Cubit has an excellent documentation about all of the different commands that can be used within Cubit, whether you type them in directly or whether or not you use them within the Python language. And I just kind of highlighted one of them right here. And we want to create a spline surface or spline curve of the points that we had in that file. And so basically what we begin to create a Cubit command string, and we put this text string in here, and then we kind of walk through. And this green command is we basically create a vertex within Cubit, and we remember that vertex ID, and we append it to this string. And after we have kind of collected together all of the points that represent our curve, we create that curve, and then we remember its ID. And we want to remember the geometry IDs, because as we have all those geometry IDs, we're going to use them later when we start meshing. So we've kind of created the shape. Now we want to go and we've stored all those that geometry information, the IDs that Cubit has been, and now we want to mesh it. And here are some sample commands that we would do. We want to set, say for instance, the edge mesh length scale. Then we want to mesh that edge. We want to set perhaps what the length scale is along the extrude direction. Set the meshing algorithms to use on the surface. Tell Cubit to mesh that surface. Set the volume meshing method. Tell Cubit to mesh that volume. So these are some sample commands that you would give within Python to kind of accomplish the meshing algorithms, and you would put all those together. The next thing you would want to do is create the boundary conditions. Just like we did with the heat exchanger, we need to create the boundary conditions, and there are commands that allow you to do that. So we create an inlet, an outlet, and this particular geometry, we're going to split the whole, and we're only going to model half of it. So we're going to have a center line, a symmetry boundary condition. So we've kind of set up all of those things, but now we have kind of used Cubit to generate, using the Python language to generate the geometry. We need to set the geometry up within Azore as well. And this is one of the benefits of Azore's database structure, where Azore has a lot of files that are human readable. And so as Azore's database is basically one input directory or a folder, depending on how you refer to those things. And it's a complex structure, but it has important things in it. And it shows the blue ones here are folders, and inside each one of these folders are different objects. And so some of these yellow folders are human readable files that can be altered by the Python language itself. So let's just look at what we might want to do. Let's just say we're going to change the material properties in the database. And so here's a subroutine that reads in the material properties and makes changes to them. So we read it in, we make the changes, and then we can do that for all of the various files within Azore and just automatically set up the whole system automatically. So we can have our whole pipeline. So that's kind of the gist of what we want to do. I thought it would be good to kind of discuss that. If running and watching a script run is not that exciting, but I have prepared a couple of scripts where we're going to actually run the Python script within Cubit, so we could kind of see what's happening here. So here we'll start, and we're going to run just the geometry creations portion of it. These scripts can be run in the background, but we're going to run these scripts within Cubit. And the first thing we're going to do is we're going to go over and we're going to read the Python script. And we're going to read one of these files, and we're just going to create the geometry. And you can see the script running here. And it's beginning to create the geometry, the volume. Now it's beginning to mesh all of the bodies. If only you could do things this quickly as a human. So it's done, and let's just take a quick look at it here. So we have kind of a hexahedral mesh at the beginning and the ending of this, as the flow would go from left to right. We have asked Cubit to put a boundary layer on the surface of our hole to improve the numerics. And we have an unstructured zone. So now I'm going to kind of stop it right here. It's like, okay, we want to do the same thing. So we want to be able to do this over and over again. What would happen if we say, actually, we want to have a different angle of attack? And that's what we're going to kind of do now. We're going to run the same script, and we're going to look at what happens if we run this script again. And in that text file, we said, actually, we have a different angle of attack. We're going to have it run there. I'm going to kind of speed through this process. We've kind of seen it working here. We've kind of automatically doing that. And if we get here, oh, wait. Huh, I wonder why that didn't do that. It's not the one that I was thinking. Oh, that's too bad. Well, you'll have to take my word for it, because it should have had the angle of attack in here. And for some reason, it's not in here. Huh. Well, anyway, you'll have to take my word for that on that. Well, but we're going to move forward here. The next thing I'd like to do is talk about this pipeline, and we're going to do it in the background instead. And so what we would like to do is we want this whole Python script to happen in the background, and we're going to demonstrate how Cubit can be run from the command line. So what we're going to do is, rather than having it interactively run, what we're going to do is run it from the command line. And so we're going to start this process right here. And where Cubit is running in the background, or running from the command line, it's doing its job. Of creating it, and now the Python script created the database. So now we're going to go into Azor, and we're going to open that database that was created. And you'll notice in this particular case, we chose a shape, kind of a teardrop shape, just as a different geometry. And we can very easily use the GUI in Azor to kind of look at the mesh topology, since we didn't really have an opportunity to look at it from the meshing side. So we can see it has similar mesh topology as before. So we do this interactive. We could have just as easily just had the simulation run. So we can see now here that the boundary condition, the material properties have been set up, or the equations have been set up. Our material properties have been set. Our boundary conditions have been set. And our outlet. So we're going to initialize the solution just like we did before. And we're going to ask to connect to it, just like we had done with the heat exchanger problem. And we're going to run on 4 processors. And once again, Azor is starting up, the GUI is starting up the background process. And you see it's run 50 iterations. So it's running right now. We can ask for the data. We can look at the simulation as it's evolving. And you can see, basically there's a low velocity zone around the vehicle. The flow is kind of traveling from left to right here. And the solution for this kind of has an interesting process. So basically the flow is kind of slowly but surely, the solution algorithm, it's slowly but surely kind of becoming attached to the hole. And once it becomes attached, then it converges very quickly. So I'm going to kind of speed things along here as we watch the solution evolve, but you'll see the residuals, they take a turn significantly downward. As the flow field kind of grows and attaches to the hole. Here it goes. So now the solution is done. So we're going to ask it to read in the solution, and we're just going to take a quick look, just like we had done before. We can easily look at velocity vectors. And pick a good length scale. The other thing maybe we want to look at, let's just quickly look at some path lines on this. So there's a lot of capabilities of looking at data here, and I just want to give a quick example of how easy it is to just very quickly visualize your flow solution within the GUI. And so that I've kind of walked through two processes of the CFD pipeline, the technology pipeline here. We've looked at one where we kind of walk through it interactively. And then we looked at another one where we kind of walked through it and we saw how we could build up using Python. And one thing I'd like to mention as well, from the Python perspective, we showed how that you could very automatically run Qubit from Python. One thing to remember also, we kind of showed running Azor kind of man in the middle, where we pulled it in and we read it. Azor, once the database is ready, it can be run from the command line just like within Python. It could be run on a cluster somewhere. So like if we were wanting to look at 100 of these different shapes, we could run Qubit, run and get 100 different input files, and then we could just kind of in a batch mode launch Azor to run on a cluster somewhere and chug away. There's no reason to go into the GUI. It was just a way of kind of visualizing that pipeline. So I think that kind of covers everything that I was looking for. I guess at this point, perhaps we can discuss if there are any questions.
Thank you, Jeff. That was really helpful. We do have a question. Can you place particles in the flow field and track them?
Yeah, those are well, not massed particles, but massless particles. That's what those path lines are massless particles. So you can kind of watch, if you were to imagine dropping a molecule and watching it flow through the flow field, that's what you would see, and that's what those path lines represent.
Thank you. I'm going to wait just another second, see if anybody else has a question, but in the meantime, Jeff, thank you so much for being with us and for leading the presentation. We were glad to have you. Attendees and those who are interested, if you'd like to learn more, the Azor website is on your screen right now, and Coreform is at coreform.com. Please feel free to reach out to us with any further questions. We do have one more. Can you look at different chemical species mixing?
Yes, you can. So you can have a mass fraction field, which is basically if you wanted to have different mixtures, and you could look and see how those go. Some of the, at the very beginning, maybe I'll just, right here, like here are some chemical species tracking, where basically you look at a plume as it comes out. This is an example of how that would be done, and Azor can do that.
Does Azor support RSM and LES models?
No, it does not. We are turbulence models. We have the K epsilon and the K omega SST. It's going to be in a release coming very shortly.
Okay. Another question, were these all steady state runs? Can you run transient cases as well?
Yes. Well, These were all steady state that we looked at here, but there is a transient version of Azor if you would like to run transient. If you have, like, say, for instance, you want to look at heat up there over time. Absolutely, Azor will be able to do transient.
Great. Thank you. That seems to be all the questions. So thank you for joining us today. Feel free to reach out with any questions. And again, thank you so much, Dr. Franklin, for joining us and leading the discussion. We'll see you all next time.